Thanks a lot to the organizers for the chance to speak at JupyterCon in this really exceptional year. I'm going to be sharing with you my vision for cloud-native repositories for big scientific data. First, I just wanted to introduce myself a little bit, since this is a virtual conference and we won't have a chance to meet at the coffee break. So I'm a physical oceanographer and a professor at Columbia University in Lamont Doherty Earth Observatory. I'm also a Python developer. I work on Xarray, Zar, and I co-founded the Pangeo Project. I'm presenting this talk to you from my basement in Burlington, Vermont. This work had a lot of input from a lot of great colleagues and collaborators, some of whom are named on this slide, and also many others who are part of our Pangeo community. In this talk, I'm going to describe two different problems and some solutions to those problems. The first problem is that scientific data is very large and complex. And the solution, one solution to this problem, is to use data proximate computing in the cloud. And I think a lot of people are doing this today. The other problem, however, is that analysis-ready, cloud-optimized data is pretty scarce, and it's pretty hard to make. This is a problem that a lot of us are just starting to confront. And so I want to tell you about one possible solution we're working on, something called Pangeo Forge. So let's start with the data. I'm an oceanographer, and I could look at movies like this all day. This is one from NASA, which just shows the richness of observations and simulations we have about our planet. So what we're looking at is an array of many different fields observed by satellite, simulated by weather and climate models. A lot of different things about our climate system, such as precipitable water. You can see hurricanes flying by. You can see ocean currents and ocean turbulence, which is the subject I study in my scientific research. And this data is beautiful and exciting and holds so much opportunity for discovery. It's also a lot to handle. This is a graph from NASA showing how their data holdings are going to evolve over the next few years as they migrate their data platform into the cloud. And you can see some arrows pointing to specific new missions such as SWAT and NISAR that are going to start producing a lot more data very soon. So that is 250 petabytes on the y-axis. And other scientific fields like astronomy and genomics, material science, are confronting very similar problems and similar data volumes. And I want to mention that this data is not only just large, but also very complex. So what do people want to do with all this data? Let me just give you a few examples. Maybe we just want to do something really simple, like take the mean. Here's the mean of one satellite data set that measures the ocean sea level. And the mean is really important because it shows us how our oceans are rising as a consequence of climate change. This is a really important graph. It's relatively simple to calculate from the data, but it does require processing all of that sea level data. Perhaps more sophisticated would be to analyze patterns of spatiotemporal variability using techniques from signal processing. So here's an image that shows the familiar pattern of the El Nino southern oscillation phenomenon that controls variability in our climate system. Of course, being 2020, what everyone really wants to do with this data is machine learning. And indeed, there are a lot of really exciting opportunities for data-driven discoveries to be made from all of this amazing scientific data that we have at our disposal. So how are we actually going to analyze all this scientific data? Well, I was raised on the download model. In the download model, what you do is you go find the data files you need out there on the internet, perhaps in the data provider's portal or website, and you download those to your computer where you clean and organize them. And then finally, you're ready to analyze the data. This is probably familiar if you work with data, this pattern, because a lot of studies have shown that the way data scientists spend most of their time is collecting data and cleaning and organizing data. And really only about 20 of their time is spent on the actual data science work of studying the data, modeling the data, visualizing the data. And that 80% is generally not considered the fun or exciting part of science. Now, this download model works just fine if your data size is measured in megabytes. It works okay if your data size is measured in gigabytes. If your data size is measured in terabytes, it can be quite painful to try and use the download model for your science. And if your data size is measured in petabytes, forget about it. You cannot use the download model at all. So a lot of people are waking up to the idea that we need to instead bring our compute to the data. And I think it's widely accepted in many fields that bringing computing to the data is a solution to many of the challenges we face in scientific infrastructure. But how? How should we do that? Well, one option is to use a platform. By platform, I mean some sort of one-stop shop where we can access our data and analyze it all in one. And a great example that many people have heard of is Google Earth Engine, which combines a catalog of satellite imagery with advanced analytics capabilities. Another similar platform is the one from Descartes, which is quite a bit newer and more of a Python native platform, very cool tool that again combines a rich data catalog with advanced analysis capabilities. The CEO and co-founder of Descartes Labs wrote an interesting article in Scientific American called The Business Case for a Data Refinery, and argued that all businesses need a data refinery to turn raw data into something that's actually useful. And I think as scientists, we really have the same problem. We need a petabyte scale data refinery. Every field these days, or many fields, need this capability. So should we just use Google Earth Engine? Should we use Descartes' platform? Well, these are great products that have enormous amount of value for a lot of people. But for academic research, exploratory science, which is what I do, I'm not sure they're the right fit. Scientist creativity can often exceed what's capable, what's built into these platforms. And then there's the question of who controls what data is ingested into these sort of platforms. Ultimately, there's also questions of whether these platform priorities are aligned with the scientific community and the open principles within that community. And finally, there's questions of cost. These platforms aren't free. Someone has to pay for them. So my colleague Joe and I thought a lot about this problem, and we wrote this blog post called Closed Platforms versus Open Architectures for Cloud-Native Earth System Analytics. And we think there's a great alternative to these closed platforms available out there. And that's what we call an open cloud architecture. So cloud computing is amazing, and it opens up a lot of interesting possibilities for how we can work with data and computing. And I'd like to propose that the future architecture for data-intensive scientific analysis and data science might look something like this. On one hand, we have data provided to us in the cloud via the object store services that those clouds offer. And then on the other hand, we're free to consume that data with computing resources of our choice, which we can configure as we see fit to meet our needs. And in the Jupyter world, we have a lot of great options for interactive computing. So Jupyter really gives us a gateway into a remote computing system, such as we can find on the cloud. And together with the amazing open source programming languages we have for scientific computing, like Python, Julia, or R, we can do amazing things with cloud computing. If we power our analytics with scalable parallel computing frameworks like Spark or Dask, we can really scale out our computing to reach that petabyte scale. Over on the other side of the figure are analysis-ready data in cloud-optimized formats, which is another, it's a key part of this vision, and that's what I'm going to spend most of my time talking about today. In order to make this architecture work, we really need analysis-ready, cloud-optimized data. And fortunately, we have a lot of great technologies and tools for that. We have tabular formats like Parquet, image formats like cloud-optimized GeoTIFF, and array formats like ZAR and TileDB. A great thing about this type of architecture is it can really be deployed almost anywhere using a very loose definition of cloud. So using all of the public commercial clouds, or in private clouds, NSF-sponsored resources like Jetstream, or you can even run a version of this stack on traditional high-performance computing systems. So I want to spend a little time defining this concept of analysis-ready cloud-optimized data. I'm going to call it ARCO data for short. So first, what does analysis-ready mean? For me, analysis-ready means I get to think about data sets and not data files. I don't have to concern myself with the minutia of how that data is actually organized into individual files. I don't need to spend time on tedious homogenizing and cleaning steps. And the data are curated and cataloged in such a way that when I sit down to work on my science, I can just immediately get to the interesting part. What about cloud optimized? So cloud optimized means that the data format is compatible with object storage. This is a key technical point, but a very important one, because in object storage, we access data using HTTP calls to the API rather than through file system calls. Cloud optimized data supports lazy access and intelligent subsetting. So I don't have to download a massive file if I only want a small piece. I can also look at the metadata separately from the data itself. Finally, cloud-optimized formats integrate with high-level analysis libraries and distributed computing frameworks. So for example, Pandas can read Parquet, which then can talk to data in an object store. Xarray can read ZAR, which then talks to data in an object store. So there's a relatively deep software stack that can leverage these formats for high-level thinking. So here's an example of what ARCO data looks like to me. This is an example from our cloud-based data catalog, which I'll say more about later. We can see this is a single Xarray data set where everything is contained in one single data set object. That object has rich metadata that gives me context to interpret my data, and the actual data itself is chunked in a way that's appropriate for analysis that allows me to, for example, combine it with a parallel computing framework like Dask to scale out my analysis. To get a little bit more specific, this is what our Pangeo stack looks like when we're working with data in the cloud. Over on the compute side, we'll be using Xarray from Jupyter, talking to Dask workers that are distributed across a Kubernetes cluster. And each of those Dask workers will be pulling data from object storage in the ZAR format. So this may be starting to look a little complicated, but what does it really mean? Well, we benchmarked the throughput we can get analyzing data and compared a legacy format and data distribution method using the OpenDAP protocol with the Xarray Dask ZAR stack. And what you're looking at is the throughput data processing rate in megabytes per second as a function of the number of parallel processes. So you can see the legacy option, it gets a little bit of parallel scaling, but ultimately saturates rather quickly at around 120 megabytes per second. With Xarray, Dask, and ZAR in the cloud, we're able to scale out our processing to 15, 20 gigabytes per second. At that rate, you can start thinking about petabyte scale processes. So in the Pangeo project, we have been putting ARCO data into the cloud and cataloging it on a website, which you can find at catalog.pangeo.io. And we've also been working with cloud providers like Google to bring climate data in analysis-ready cloud-optimized formats to public datasets programs, as we recently did with the Climate Model Intercomparison Project. And in doing this, we've realized there's a big problem facing our field if we want to realize this vision of cloud-native science. The problem is that making ARCO data is actually quite hard. We're expecting a lot from our data scientists in asking them to produce this ARCO data. Let me unpack that a little bit. So in order to produce useful ARCO data, the person producing it, most likely a data scientist or scientist of some sort, has to have the following skills. You need domain expertise. You need to know how to find, clean, and homogenize the original data. You need a lot of tech knowledge. You need to know how to efficiently produce cloud-optimized formats. That means being current in things like ZAR, Dask, and the latest cloud technology. You need significant computing resources. You need a place to stage and upload this ARCO data from. And a lot of people are doing that on their own workstations right now. And finally, in order to make this data useful, you need a lot of communication skills to explain to other people where to find your ARCO data and how to use it for science. And there are just not a lot of people out there who have all of these skills. And even if there were, asking individual scientists to contribute data like this is not really a scalable way to populate a cloud-based data repository. So we have a real problem. So the idea we've had in our Pangeo project is to try to crowdsource the production of ARCO data. And our effort to do this is called Pangeo Forge. And this is deliberately inspired by the very popular Conda Forge technology that many of you probably know. So let me try to explain this analogy. Conda Forge is an amazing tool which democratizes and crowdsources the production of Conda packages, which so anyone can contribute a recipe to Conda Forge, which is then using cloud infrastructure and continuous integration, is built into a package that can be downloaded and installed anywhere. And it's really opened up the data science space and made it a lot easier to distribute software. So we'd like to be able to do the same thing with data. We'd like a data scientist to have to bring only their domain expertise on where to find interesting data, and Pangeo Forge to take care of the technical problem of transforming that data into an analysis-ready cloud-optimized format and placing it in cloud object storage. So this isn't just an idea. This exists. So we are working on building Pangeo Forge. And if you want to learn more, you can go to the Pangeo Forge GitHub organization and read our roadmap. I'll just tell you a little bit more about the details of Pangeo Forge. It's pretty complicated. So data is complex and there are a lot of edge cases. What I'm showing you here is a diagram that I'm not going to explain in detail, but I'll just say that the aim of Pangeo Forge is to fully automate the process of extracting data from its primary repository, transforming it into an analysis-ready format, and depositing it into cloud object storage. And our main goal is to use, or one of our goals is to use GitHub as the primary point of orchestration and communication among scientists and data engineers. So currently, Pangeo Forge consists of a couple different ingredients. There's the Pangeo, and these are each GitHub repositories. There's Pangeo Forge itself, which is a central workflow manager and API for producing these data sets. We have Pangeo Smithy, which is again modeled after Conda Smithy, which is a tool that actually will produce these data sets using the Pangeo Forge recipes. Now, the recipes are stored just like Conda Forge in various feedstocks. So an individual feedstock would consist of a recipe to extract data, transform data, and load it into the cloud. These feedstocks are designed to be the real central point of collaboration. Each data set will get its own feedstock. And within this, we can version control the pipeline and discuss and publish the details of how the data are transformed. And then we can use we can use the Pangeo Forge technology, Pangeo Smithy, to actually run this pipeline in the cloud. And in order to run those pipelines, we are using PREFECT. So PREFECT is a new data engineering tool that we found is a perfect match for what we need to do in Pangeo Forge. So currently, we are using PREFECT to deploy these recipes and extract data and stage it and build it into these ARCO data sets in the cloud. So there's a lot of work left to be done, but I think we're in a pretty exciting point in this project. So I'm just going to summarize that if you're feeling the pain of large, complex scientific data, data proximate computing in the cloud can be a great solution. And open cloud architectures can enable us to use cloud computing while staying true to open source principles and facilitating transparency and reproducibility. Problem is that analysis-ready cloud-optimized data is hard to come by and difficult to produce. So we hope Pangeo Forge will make it easier for people to contribute ARCO data such that we can collaboratively populate cloud-based data libraries. And in order to make this project succeed, we really need your help. So I want to encourage anyone who's interested in this problem to come talk to us on GitHub and see if there's ways we can work together to realize this vision. Thanks a lot for listening to my talk.